Welcome to the lesson activities for differential equations. This is for section 3.1, part 2 of the lesson. Consider the second order ODE that models an undamped harmonic oscillator. Y double prime equals negative y. Guess and check until you find two particular solutions to this ODE. Think trig. Okay, so I'm looking for a function whose second derivative is the opposite of itself. So if I'm thinking trig, let's try sine. If I let y equal sine t, then y prime is cosine t, and y double prime is negative sine t. So it does work that y double prime is the opposite of y. So, and then let's try cosine. So if y equals cosine t, y prime is negative sine, and y double prime would be negative cosine. So y double prime is in fact the opposite of y. Y double prime is the opposite of y. So we have two solutions. We'll call them y1 and y2. Two particular solutions. Okay, convert the second order ODE to a first order system. So we always start this by letting y prime equal v, because we always think of this as y is position, y prime is velocity, y double prime is acceleration. So if y prime equals v, then y double prime equals negative y, and I think that's all we have to do. I'm sorry. Instead of y double prime, we're going to call that v prime, so that we have a first order system where we only have first derivatives. Okay, write the first order system using matrix notation. So we have y prime, v prime in a vector equals, then we have our ABCD coefficient matrix times YV. And I want my first equation to be 0y plus 1v. So I've got a 0 and a 1. And then my v prime equation is just negative y, so negative 1 and 0 v's. Write a vector y1 of t that solves the system that we wrote down in part C and represents the first of the two solutions we found in part A. Okay, so y1 as a vector of t, that is y1 v1. So we already know y1. We found a solution to the second order equation. It's the same, because this second order equation is exactly the same as the system. They're just representing the same undamped harmonic oscillator in two different ways. So I already know one solution, y1. So I have sine t. And then v1 is just the derivative because y prime equals v. So v is just the derivative cosine t, because velocity is the derivative of position. Okay, and then we're going to do the same thing for y2. So I'm going to have a vector solution y2 of t, which is really y2 v2. And y2 we said was cosine t, and the derivative of cosine is negative sine. Okay, now we want to evaluate y1 of 0 and y2 of 0. So I'm plugging 0 in for t into the vector valued functions y1 and y2. So y1 of 0, that would be sine 0, cosine 0, which is 0, 1. And then y2 of 0, that's cosine 0, negative sine 0, which is 1, 0. Okay, write down the general solution to the system you wrote down in part B. So because my y1 of 0 and y2 of 0 vectors are linearly independent, because one is not a multiple of the other, That means that my solution, my general solution, y of t, will have the format k1, y1 plus k2, y2. And I can now just put in y1 and y2. So I have k1 times y1, which is sine t cosine t, plus k2 cosine t negative sine t. Find a particular solution to the system that satisfies the initial value y of 0 equals 1, 2. Okay, y of 0 means just plug a 0 in for your t's. So we have k1 times sine 0 cosine 0, which is 0, 1, plus k2 times cosine 0 negative sine 0, so that's 1, 0. And we were given that that equals 1, 2. So then I can translate this to two equations. This says 0k1 plus 1k2 equals 1, which tells me k2 is 1. And the other equation is 1k1 plus 0k2 is 2, which means k1 is 2. So my particular solution is going to look like this, but I now replace k1 with a 2 and k2 with a 1. So I didn't give myself quite enough room to do this. I'm going to write it in the space where I is right now. So it's going to be k1, which is 2, times sine t cosine t, plus k1, which is plus k2, which is 1, times cosine t negative sine t. So that's my particular solution. That's the answer to part H. Okay, so part I says write out the general solution to the system. Write out the general solution to the second order ODE, y double prime equals negative y. So we can find this answer in part H. In part G. Because the solution to the second order equation is just a y, whereas the solution to the system is a y and a v. So the first entry in this solution is y. The second entry here is a v. So for I, if I just want the y, I can just grab it. So I'm going to have y of t not vector valued, no arrow over it, would just be k1 sine t plus k2 cosine t. It's just the y from my yv vector valued equation. Write out the particular solution to the second order ODE, y double prime equals negative y, that satisfies the initial condition y of 0 equals 1. So hint, this can be found in your answer to part H. So I only want the y, right? I already have a particular solution that satisfies y of 0 equals 1, because this is y and v of 0. Y of 0 is 1, v of 0 is 2. So this initial condition I solved down here, but the first entry is y and the second entry is v. So I don't have to actually do any work to get this. I can just write y of t is 2 sine t plus 1 cosine t. Okay, so for number 2, we're going to consider this linear system and the vector valued functions y1 and y2. And we want to check that these two functions are solutions of the system. If they're not solutions, we stop. Okay, before I even start trying to check, I'm just going to translate everything that I'm given. It's given in vector and matrix notation. I'm going to translate a little bit to equations. Take it out of this notation and put it into one that we're more familiar with. Okay, so my differential equation system up here, I'm going to translate that. So I'm going to have That y prime is bold, which means that it's like a drop-down menu. It's a vector full of things. So we're going to call that x prime and y prime equals -2, -3, 3, -2 times bold y, which is a vector that has an x and a y in it. And then if I translate this to equations, it says x prime equals -2x minus 3y, and y prime equals 3x minus 2y. Okay, so I've translated that. And then I'm going to translate my potential solution y1. So y1 is a vector, which is really an x1, y1. It's a vector that has an x and a y in it. And then this has two entries. They're separated by a comma. Your book does this a bunch, so I decided to give you a problem where I wrote it horizontally, so you can get used to it. I'm going to translate it to vertical notation because that's what we're more used to. So we have e to the -2t cosine 3t is the first entry. And then the second entry is e to the -2t sine 3t. Okay, so that means as separate equations, x1 is e to the -2t cosine 3t, and y1 is e to the -2t sine 3t. So I want to know, did these functions satisfy these differential equations? So I'm going to have to get an x prime and y prime. I need to figure out the derivatives to put in here. And then I want to know, does the derivative of this equal -2 times x minus 3 times y? And I'm going to need all the space. So I'll get a new page for y2 if I need it. Okay, so x prime, x1 prime, I'm going to have to do the product rule to get this derivative. So I have first times the derivative of the second plus the second times the derivative of the first. So there's my x1 prime, and then my y1 prime is first times the derivative of the second plus the second times the derivative of the first. Now I'm going to plug everything in. I'm going to plug in my x prime and my y prime that I just found, and my x and my y that I was given, and see if these two equations hold true. So let me rewrite the equations where we can see them. X prime is does x prime equal -2x minus 3y? I want to know, is this true? And then I'm going to come back and do the other equation after this. Okay, so x prime, I calculated it up right here. So I'm just going to write down what x prime came out to be. We have e to the -2t times -3 sine 3t plus cosine 3t times -2 e to the -2t. Does that equal -2 times x? X is this, right? That was given. E to the -2t cosine 3t minus 3 times y, and y, so that's the -3 times y, but y is this function given. E to the -2t sine 3t. Okay, are those equal? So this term is the same as this term, and this term is the same as this term, because you can do multiplication in any order. So these are, in fact, equal. Okay, so the x1 seems to work, but to be a solution, x1 and y1 both have to satisfy the system. So remember that the equation for y prime was, just gonna scroll up and look, 3x minus 2y. Okay, so y prime, we calculated it. It was e to the negative 2t times 3 cosine 3t plus sine 3t times negative 2e to the negative 2t. Does that equal 3 times x? So 3 times x, which is e to the negative 2t cosine 3t, minus 2 times y, and y is e to the negative 2t sine 3t. So are these equal? So this term with the negative 2 corresponds to this term. They are the same. And then this term corresponds to this term because you can do multiplication in any order. So these are equal. Okay, so yes, y1 is a solution. The bold y1 is a solution. Then we have to do this whole thing again with y2. We have to go through this whole analysis again with this new potential solution, another potential solution. Okay, so now I'm going to repeat this entire process using a new potential solution, y2, same differential equation. Okay, so first I'm going to translate y2 into two different functions, an x1 and a y1, that I can test in my differential equations. So this is actually x2, y2, and it equals two entries, e to the negative 2t times negative sine 3t is the first entry. And then the second entry is e to the negative 2t cosine 3t. So x2 is negative e to the negative 2t sine 3t. So let's start here and calculate the derivative, x2 prime, using the product rule. So we have first negative e to the negative 2t times the derivative of the second, which is, the derivative of sine is cosine, and then because of the chain rule, we have a 3 cosine 3t. Okay, so it's first times the derivative of the second plus the second times the derivative of the first, which would be 2e to the negative 2t. All right, so let's start there. Actually, let's get y. Let's do y first. So y2 is e to the negative 2t cosine 3t. Just copying that down from y2 is this. x2 is this. Okay, so y2 prime, we calculate the derivative, and we have first times the derivative of the second plus the second times the derivative of the first. Okay, so now that I have x and y, and x prime and y prime, I can plug all of that into these two equations and make sure they're both true. All right, so I'm going to start with x prime. Does that equal negative 2x minus 3y? All right, so x prime is this up here. So that's negative e to the negative 2t times 3 cosine 3t plus sine 3t times 2e to the negative 2t. Does that equal negative 2 times x, where x is this function here, negative e to the negative 2t sine 3t, minus 3 times y, where y is e to the negative 2t cosine 3t. Okay, so are these the same? So this term right here, we have the negative and the negative, so that would become just a positive 2. So this term and this term are the same. And then here I have negative 3 e to the negative 2t cosine 3t. And that works here. It corresponds to this term because we've got the negative and the 3. So these are, in fact, equal. Okay, so the x prime equation holds true. Still have to check the y prime equation. Okay, so y prime is supposed to equal 3x minus 2y. So y prime we calculated right here. So we have e to the negative 2t times negative 3 sine 3t plus cosine 3t times negative 2 e to the negative 2t. Does that equal 3 times x? X is negative e to the negative 2t sine 3t minus 2 times y, and y is e to the negative 2t cosine 3t. Okay, so are these in fact equal? We've got a negative 3 e to the negative 2t sine 3t term right here, and we have that same term right here. And then I have negative 2 e to the negative 2t cosine 3t term, and this term is the same as this term, so these are equal. Okay, so that means that y2 is also a solution. y2 is also a solution. Check that the two solutions are linearly independent. If they are not, we stop, but we can still check. Okay, so that means to have linearly independent solutions, that means that if you plug in 0 into both, you get linearly independent vectors. So y1 of 0, if you put a 0 in for all the t's, this t and this t and this t and this t, this becomes a 1. Cosine of 0 is 1, so 1 times 1 is 1. And then this is a 1, and this would be a 0, so 1 times 0 is 0. And then y2 of 0 would be negative 1 times 0, which is 0, and 1 times 1, which is 1. So 1, 0, and 0, 1 are linearly independent. It's easy to determine when you have just two vectors. One is not a multiple of the other, which means they are linearly independent. Okay, find the solution to the linear system with the given initial value. So I'm going to start by finding the general solution. So the general solution, when you have two particular solutions that are linearly independent, the general solution is a linear combination of those two. So we can just do k1 y1 plus k2 y2. Okay, so this is k1 times y1, which is e to the negative 2t cosine 3t, e to the negative 2t sine 3t, plus k2 times y2, which is negative e to the negative 2t sine 3t, e to the negative 2t cosine 3t. So there's my general solution. Okay, so you'll notice that I didn't actually give you an initial condition here, so I'm going to add that in. This may be why you're watching this video. How am I supposed to do this without an initial value? You can't. So I'm going to tell you that y of 0 is 2, 3. And we can use that initial condition that should have been given ahead of time to find k1 and k2. Okay, so y of 0 will give me k1 times 1, 0 plus k2 times 0, 1, and that's supposed to equal 2, 3. That tells me that k1 is 2 and k2 is 3, which means the solution I'm looking for looks just like this one, but replace k1 and k2 with those values. So my particular solution I'm looking for is y equals 2e to the negative 2t. It's okay if you leave the e to the negative 2t's in the parentheses, but since it appears in both the top and the bottom, both entries, we can pull it out here. And then all we're left with is cosine 3t and sine 3t. And then we have plus k2, which is a 3. And again, I can pull out an e to the negative 2t. And what's left inside is negative sine 3t and cosine 3t. And there's my particular solution.